Excellent. Okay. All right, so let's talk a little bit about expert elicitation for structure. Okay, so structure is just the arcs and the relationships. Okay, now one of the approaches to doing this is starting off with a conceptual model first, and then moving to a BN. It's kind of a matter of preference whether you do that or start directly with the BN. My preference is not to use a conceptual model. I think it's good to start off with the right ideas and concepts from the very beginning. Essentially, your initial model is your concept model, but you're at least being a little bit rigorous about how that model's put together. And then you can throw that away and start building again. So if you think about the prototyping process, you've got that very small initial model. You can treat that as your conceptual model and then grow it into the real system later on. So there's some terminology around conceptual modeling. Whether that's useful or not, I don't know. That's up to you. But there's different terms around. So sometimes it's called mental models. Sometimes it's called conceptual models. Sometimes it's just basic brainstorming or whatever. There's different kinds of terms around it. But basically the idea is, always the same. You're starting off with a basic simple model, and then you're expanding that in some way. Okay, so there's many ways to do conceptual modeling. Obviously a whiteboard, or a pen and paper, just scribbling stuff out is a very good way to start. You've got software tools that are dedicated to conceptual modeling. CMAP was one that was well, it's still around and it was popular a little while back. There's probably other tools which are a little bit better for doing conceptual modeling now, although CMAP's quite good for BaseNet specifically. And of course there's the BaseNet tools themselves. So you can quickly, if you choose the right tool, you can quickly put your nodes in there, put in your arcs. Don't bother with probabilities or anything like that. Just put in notes next to your nodes, and that works just as well. Okay, so when you're doing a conceptual modeling process, you've got to start off with your, obviously your research topic, whatever it is that you're interested in. So that's not necessarily your objective, it's just the kind of area that you're interested in. So you want to do a little bit of research ahead of time to work out how that domain looks and what kind of questions you might be interested in. So then once you've done a little bit of that research, then you can settle on and say, okay, I've got a good sense of what question to ask. And what I'm interested in. So that's what you want to do next. Once you've done that, you then want to go through and identify the key concepts that you think are going to be involved in your model. Okay, these will relate to the nodes that you want in your model in some way. Either, they'll be identical to those nodes, or they'll have to be broken up into some kind of submodel or something like that. You should organize them in some way. This is like an object-oriented kind of idea. You want to group different nodes which are related. If you've got multiple entities, you want to organize those nodes by the entities within that system. And then once you've got a list of all your variables, you want to rank them and say, okay, which ones are really critical to producing a good model, and which ones are, they might be useful and might bring in later, but we won't start with those. Okay, so concept maps are basically initial Bayes nets. Okay, so they represent the concepts in the system. You've got the major ideas represented. You should have, again, lots of documentation at this stage detailing what it is that you're thinking, what your experts are thinking and are important as well. Don't quantify any relationships at this stage. You want to identify the relationships. You want to say, okay, there's, these two are connected in a or-ish type fashion or what have you. So, either of these causes might contribute to the effect, but you don't want to quantify. You don't want to start getting hung up on any numbers at this stage because you can fossilize the network a little bit too early. Definitely don't use them for decision making because they're just very crude approximations. Although, admittedly, if you've got nothing better, then that's what you should use. And they can be used then to guide the process, your future processes. So as you're building your Bayes net, you're basically either evolving it directly from your concept model or you're using it to guide how that model's built. Okay, so let's say we've gotten to the the stage where we say, okay, we've shifted beyond just concepts, and we want to go beyond just mapping out the domain, and we want to actually start building something that's useful and usable. Okay, so the process for doing that, there's many different ways of doing that, but there's a couple of common features to each of those. So again, you've got your key kind of question that you want to answer, or get some kind of idea about. That key question, basically, is either going to be your target node in the network, so your focus or your query or your target node. There's lots of different names for it, but I usually use the term target node. Or there might be multiple target nodes, okay? For a lot of these kinds of things, there probably will be a single target node for a lot of these kinds of models that you're going to be helping people build. So it might be good to, when you're building the interface for these things, to have that kind of in mind, where you've got one or a very small number of target nodes. And I think that will probably drive the way the interface works a little bit. Okay, so you've got lots of other variables in your network, other variables that may impact on your target node. They generally broadly fall into two different categories. So there's the observable nodes and the unobservable ones. Now you might say, well, why are we bothering putting in unobservable nodes? Basically, that's so that we can capture, that causal story that Eric was talking about yesterday in more, more faithfully. And it's a lot easier for then experts to then sit down and reason through the network if you've got an accurate depiction of the real system than if you've just got what's observable and some statistical connection to the, the target variable. But you want to know what you can observe. That's very important, and what you can't observe. All right? You've got your context variables, so that the context variables might not be directly related, to your model, and sometimes you can assume them in your prior probabilities. But sometimes it's useful to explicitly flesh out the background context as well. And then you've got the variables that you can control. So typically you would be doing that with decision nodes, but you might actually create a probabilistic network and say, well, we can control these nodes here, but we're going to model it as if we have no influence over them. So you have to work out which variables are the ones that you can control. Okay, so I think the key point, in order to constrain the network that you build, is to start off with the target variable or the query variable and spread out from there. If you start from your background variables or your observables, you're likely to get a huge knotty network that doesn't actually answer the problem that you're trying to answer. It doesn't solve anything for you. Or alternatively, it does, and it also answers 500 other questions that you don't care about. That's a waste of time, and you want to focus on what's useful. So you want to start with your target variable. You spread out, either spread back, and say what can cause, what are the ancestral causes of this target variable, or you want to spread forward and say, what are the descendants, what are the future possible consequences from it. And of course, with the iterative prototyping approach, the role of variables can change all the time. So you might decide that, well, actually, we can now do observations with this particular variable. Or you might say, okay, actually, we weren't interested in this target variable. That was actually a proxy for the real target. So we want to focus on this other target. Okay. So when you're creating variables, there's various rules. In some sense, these are enforced whether you like it or not. But okay, variables need to be mutually exclusive, so in terms of the states, and exhaustive. Okay, so typically, if you're creating, say, for instance, a Boolean variable, simple Boolean variable, then you've got two possibilities. They define the only possibilities that can occur for that variable. So they're exhaustive, and they're mutually exclusive. So you don't have some middle value, that you can't possibly have between the two. Now, it's important to get this right. Sometimes it's not always obvious how to get this right. So, for instance, in terms of mutual exclusivity. So, for instance, if you had you're trying to work out what kind of a disease a patient has. That disease variable might have, you might create a disease variable and it might have multiple states, and you might say, this person might have malaria or measles or some other disease, diabetes, and so forth. And then you have a single variable for that, but those states aren't mutually exclusive. A person can have multiple ones of those disease. And if there's a significant chance of overlap, then it's going to create major problems when you do your inferences. So you have to make sure that they're mutually exclusive. So in that case, you would break them out. So you'd have one node for malaria, one node for measles, and so forth. Yep, makes the network a lot more verbose, but you need to do that. Okay. The other thing is that it needs to be, your variables need to be exhaustive. So say, for instance, you had a variable for the color of some object. That might have a couple of states. You might say, oh, the color of this object can be red or blue. Now, if it can only ever be red or blue, that's fine. But if it could take on some other colors, say, for instance, green or orange or what have you, then you're going to run into problems again. Okay, so the simple solution for that is to have, say, for instance, if the two major colors are red or blue, you would say, okay, you've got red, blue, and other, some other color, whatever other color. And that's all covered in that final state. So that it's critical to do that, again, because otherwise the inference goes awry. Okay. Okay, so you have multiple types of variables. For the most part, we've only seen, binary variables or, three valued variables or so forth. So we haven't seen, particularly different kinds of variables so far. But you can have lots of different kinds, so you can have lots of different states. They can be of a particular ordered arity, so they can be pseudo-continuous in some sense, or they can just be categorical, just naming different types of things that they can be. Or it could be a qualitative variable, so that's a little bit different. You might be saying, okay, this is, in some sense there's a quantity associated with this, but we're not going to delve into what that quantity is. So we might say, okay, all we're interested in terms of, say, speed is not the actual value of the speed. We just want to know if it's increasing, staying the same, or decreasing, and that's all we care about. Okay, and of course you've got numeric discrete variables, something that could only take on a specific number of values, and often for that you might, if you're creating larger networks, you might create a Poisson distribution over that, or a binomial. But in a simple kind of network, you might say, okay, you can only have 1, 2, or 3 of this item, for instance, or other, to make sure it's exhaustive. And you can also have numeric continuous variables. So you can say, well, speed, for instance, can be any value between 0 and infinity. Usually those are discretized. Okay, so continuous variables are almost always discretized in all of the software, and you won't encounter too many continuous variables in the arguments, the models that you're going to be helping create. So yeah, it's possible that further down the track you might want to allow for continuous variables in some way, but I would say it's probably a distraction in the case of BARD. You want to focus more on the categorical variables, simple numbers of states, just to keep things simple. Okay. So the goals with creating the graphical structure of the network, the main goal in most cases is to maximize the fidelity with the actual target system. Okay, so you want to say, we only want to have arcs where there's a genuine cause in the system, and we don't want to have arcs there if there are no genuine causes. That's not always possible. Sometimes you just want to simplify the network and create a statistical connection and not bother about faithfully representing the system. Sometimes you do want to do that, but almost always, as Eric was saying yesterday, you want to start off with the assumption that you're going to build a fully causal network. That doesn't mean that you have to build a completely precise model of the system. So you don't have to create this, extravagantly large network that models every single aspect, every cause within the system. You have to make sure that you're picking the right level of description. Okay, so you're saying, I want a model that's really simple enough, but still explains the system. So simpler and no simpler. So in terms of the there's various advantages to doing it in the a causal direction. We saw some of that in the exercise yesterday. So if you created your model causally, a lot of the questions that you have to ask about parameters are much more logical and a lot more intuitive. And usually you get a more compact network. You actually end up with fewer parameters that you have to elicit. If you've done it the wrong way, you usually have to add in additional arcs to represent the things you've missed. And that can complicate the network. So that's often a hint that you're not doing it right. If things are really complicated when you get to the parameterization stage, or if you've just got far too many parameters, you've probably modeled incorrectly in terms of the causal story. Okay, so relationships within the structure. So you've got some arc structure across the network. But the arc structure doesn't really describe what the relationships are. You could define parameters which mean that parents are entirely neutral. Okay, so if you leave your CPTs uniform, doesn't matter what state that you set your parents at, it has no influence on the child. Okay, but you can set those numbers to define essentially any relationship that you want between those two parent variables and the effect. Okay, so you want to identify what kind of a relationship is it. So if you're thinking in terms of logic circuits, for instance, you might want to say, okay, is it an OR relationship? Is it an AND relationship? Is it an exclusive OR? So forth. So those are the kinds of relationships that you want to apply to, say, very simple binary variables. The relationships in Bayes nets end up being a little bit more complicated, but there's certain analogs that you can use to actually simplify things, which I'll talk about shortly. You want to think about, okay, is one parent variable, say, act like a catalyst for other parent variables, so that it enables them or it improves the effect that they have on the child? Or do they act as an inhibitor? So does this variable essentially control whether the other parents have any effect or not? So it can be useful to identify that. You want to look at your parents for your variable, and you want to say, well, do they interact when in their effect on the child, or do they act independently on the child? That has an enormous impact on the simplicity of the network. If you can identify that a relationship between parents is independent, then that simplifies things a lot. You want to see if there's any relationships between the parents, for instance, if there's any explaining away relationships. Usually you realize this after the fact. It's not something that you start with as a constraint. But sometimes you might say, okay, these two variables are not going to be true at the same time. And you want to look at essentially other forms of independence, causal non-interaction, whether parents are in an additive relationship or multiplicative relationship or what have you. Okay, in terms of causal interactions, you might want to look at if the parents interact in such a way that they produce a synergistic effect, either positive or negative. So two parents might have an effect which is greater than the two parents alone, or they might have a lesser effect. So the sum of the parts is essentially greater than the sum of the parts or less than the sum of the parts. You want to see if they interfere, if there's an exclusive OR relationship. You also want to look at your variables and say, okay, are certain variables screened off by other variables? Maybe there's a long causal chain that relates X and Y, and there's some variables in between that should screen off X and Y. So you want to look at those kinds of things. And essentially, you also want to look at the dependence relationships, and you want to say, well, if I learn something about this, it should update my belief about something else. And you want to check that the network actually does reflect that. So that's a concept which makes use of a concept called D-separation, which we'll look at a little bit more in the session later this afternoon. Okay, so there's various modeling tricks. You'll pick up a lot of different modeling tricks as you're going through and working with BNs. I'm not going to cover the whole gamut of the different kinds of modeling tricks that there are, but we'll just take a look at one which is particularly useful for producing compact BNs. Okay, typically when you create, especially when you're starting with that method of starting with a target variable and working backwards. One of the issues that you can get is you can get a lot of parents into your target variable, for instance, or, and that can be really bad because the CPT blows out of sight. So you've probably seen already that CPTs can grow, you know, a little bit large when you've got a small number of parents. That's nothing in comparison to what happens when you've got large numbers of parents and large numbers of states. So you've got, say, for instance, a node here, and you've started with this node, and you go, well, what can cause, you know, the health of a person, for instance? And you can say, well, the temperature, weather, mental health, so forth, they all contribute to the health at some point in time. So that might be your initial model. You might start off with that, and you're not trying to work out in too much detail what's going on, but it's kind of a concept map, essentially. But once you've done that, you want to start analyzing things in more detail, because if you try to parameterize this, it's going to be a huge mess. Okay, very few experts are going to be able to do it, and even if you've got some equation to define, you know, what's going on here, doing the testing on that is a bit of a mess. So you want to break it down, and you want to say, okay, well, you know, we can lump different things together. We can lump temperature and weather together. Together they produce wind chill, and the wind chill will, you know, produce hypothermia in a person, and that's what affects the health of a person when we find them. And then you can group these other ones together in a similar manner. So you can kind of break things up so that you haven't got quite so many parents going into a node. So a good rule of thumb for the number of parents going into a node is probably on the order of no more than about 4. Okay. Again, if you've got a continuous network, it's a different thing. You can probably put as many as you want, but it becomes more difficult to analyze as to what's going on. So, yeah, no more than 4. If you can get away with 2, that's really, really good. And you can always get away with 2 because you can always divorce it down to 2. But you may lose a fair bit of the accuracy in terms of the interactions. So. Okay, so let's do an exercise, a quick exercise on that modeling trick. So, okay, so I think everyone's had to think through that and come up with a couple of different kinds of solutions. So there's more than one way generally when you're divorcing parents to handle a problem. Sometimes it's obvious because you've got 2 parents which are, you've got one parent which is independent of other ones, so you can, easily divorce that or so forth. But sometimes you just want to simplify the network. There's connections between all of the parents. You're going to lose accuracy, you know that, but you're happy to wear that in terms of when you're doing the divorcing. So, okay, so here's one possible solution. Is that right? That's your solved network? Yep. Okay, so you've got here, so we had the original node over here, crop yield. Its parents originally were pesticide use, drought conditions, annual rainfall, and irrigation. So what we've done is we've introduced something to model the state of the crop water, whether it's good or poor, and just focused on what influences that. So that's drought, rainfall, and irrigation, because they're all kind of ideas about water. And we've summarized it here in this node here. And then over here, we've divorced the pesticide use off, and so the CPT for this one is going to be a lot simpler. It's just got the 2 parents, and this one will be a little bit simpler as well because you've just got the 3 parents instead of the 4. So there's a couple of other possible ways that you could divorce the parents. So say, for instance, Greg did pesticide use and drought, and put them into a separate node, which was essentially what are the negative influences on the crop yield, and then tied together the annual rainfall and the irrigation. So what are the positive water influences, the inflows. So you could do that that way as well, and that would probably produce a network which is a little bit simpler in terms of the number of parameters in that case. So if that maps well to what your experts are thinking and the way they think about the model, then that's probably something that you would prefer to do. But if they prefer to think in terms of the water aspects of the system, you'd probably use this kind of a model instead. So there's multiple ways. Even those 2 ways are probably certainly don't exhaust the set of possibilities. But the idea is to produce a simpler network. Often you work towards a more causal network when you're doing it. That's not always the case. Sometimes you're just trying to get a network that runs, and so that's why you're doing it. And so you lose accuracy in that case. But there's essentially multiple approaches. So, but this is something that you will probably want to build in some kind of support for in the tool. So there's going to be a lot of refactoring in the tool. As people learn more about the problem, discuss things with each other, and work out how a model should look, you want to make it as easy as possible to refactor those models. Okay?